Hi everybody, welcome to my office hours. You might hear some stuff in the background, but that's because I'm raising kittens and they are right now just running around my room. So you may hear some noises or little tiny meows from them like that, if you heard that. But anyways, so today we're going to be going over chapter 3 and chapter 4. These are my second office hours. I'm doing them on a Thursday instead of a Friday because tomorrow, which is Friday, I'm going to be going out of town. So I will be doing my office hours today. I'll be recording them and uploading them just as usual. If you're watching this on the recording, then obviously you found that out. All right, so let's start with organic molecules and functional groups. Now, this chapter is probably the least important chapter in all of our book, in my opinion, because all it's teaching you generally solubility rules, boiling point rules, and how functional groups are actually going to be attached to a carbon. A lot of these functional groups you'll end up seeing in the future a lot more, and you'll be able to tell which one is which a lot easier. I wouldn't say memorize any of them for now, except for, like, if you do end up memorizing them, save that to the last of your studying, in my opinion. And I would say memorize the, definitely know the difference between alkane, alkene, and alkyne. You don't really need to know as much about an aromatic compound, except to know that it's called a phenyl group when you're naming it. And then also know primary, secondary, tertiary, and quaternary carbons and primary, secondary, tertiary hydrogens. To review, a primary carbon is a carbon that's attached to one other carbon. So like the bonds around it can either be hydrogens or nitrogens or oxygen. It could be whatever as long as it's not another carbon. A secondary carbon is a carbon that is attached to two other carbons. Again, these bonds can be anything else. Tertiary, 3 carbons, quaternary, 4 carbons. And it's a little bit different when we're talking about other types of atoms attached to carbon. When you have a hydrogen attached to a carbon, it's a primary carbon if the carbon it's attached to is attached to one other carbon. So like, let me draw something real quick. So something like CH3H, and then like O. This hydrogen is a primary hydrogen. This one's also a primary hydrogen. Okay? And then a secondary hydrogen, it's as if this carbon was attached to other carbons, two other carbons. So like, let's say that instead of an oxygen here, we had another CH3 right there. Thank you if any of you said bless you to your screen. This hydrogen here, now it's a secondary hydrogen because it's attached to two other carbons. The carbon is attached to two other carbons, and then tertiary if this hydrogen was a carbon instead. Okay, I think that's pretty clear in itself. Like if I were taking the test, it might ask you like, I guess, maybe it would be like, what kind of carbon is this? And you'd say, oh, it's a tertiary carbon or a secondary carbon, or what kind of hydrogen is this? Primary, secondary, tertiary carbon. Oops, that is not what I meant to do. Stop annotating. And so, okay, so here are like some important-ish functional groups. Like I said, I would leave memorizing functional groups to the end of your studying because honestly, I think it's less important. The main question that I might see on a test, or if I were making a test, I would put on a test, is I would give you like a large molecule. Like let's say I gave you something like this. And I was like, so what kind of functional groups do you have here? And then you'd be like, oh, I have an alkane because I have I have an alkene because I have a carbohydrate with a double bond. I have an aromatic group, which is also known as a phenyl group. I have a, hold on, let me change this real quick so it's a little bit clearer. I have a ketone and I have an alkyl halide, where, and then we can look here at the different ones that we have here. Alkyl halide, that just means we have an alkene with a halogen at the end, where our Br is the halogen. Our ketone is just when we have a double bonded oxygen that is attached to two other carbons. So this carbon here is attached to two other carbons. And then the alkene is just anything that has a double bond between two carbons. And then our phenyl group, that's our aromatic group. So that would be like something that you might see on a test where it's like list the functional groups that are present in this compound. But again, I recommend doing this last in your studying. Functional groups with CZ sigma bonds, all that means is carbon single bonds. So like an amine has a carbon single bond to a nitrogen. And then like I said, all these functional groups are important, but they're more important in later chapters. Like most of this C double bond O stuff, that's more important in Orgo 2. And then we don't really talk about phosphate groups at all unless you're in like biochemistry or something. That class will focus more on phosphate groups and how they work. So now we're going to be talking about intermolecular forces, just like a quick review of intermolecular forces and stuff from your Gen Chem. So our strongest molecular force is going to be hydrogen bonding. So this is a hydrogen bond between H and N, H and O, or H and F. Okay? And then we're going to be worried about dipole-dipole moments, so I'm going to put dipole. So all this means is electronegative atoms. So you can see here in acetone, in this example, we have oxygen, which is an electronegative atom, next to a carbon. Since those are significantly different with their dipole moment, or since their electronegativities are significantly different, they're going to have a dipole moment, and that's going to make that bond stronger. And then finally, we're going to have something called van der Waals. This is just basically the random movement of electrons around something where it attracts itself to itself. So like it's as if we had like two carbons right here, and one of them had all of its electrons on one side. So like one side of it was negative, one side of it was positive, and then this had the same thing. And this is possible because electrons can be anywhere at any time, but that's just basically van der Waals. Every single type of molecule has it. So isobutylene here, it has van der Waals. It does not have dipole moment. Acetone here, it has van der Waals and a dipole moment, okay? And so then this comes into handy when we're talking about solubilities and melting points and boiling points and stuff. The stronger the intermolecular forces, the higher the boiling point and the melting point is going to be. And if the molecule is polar, it's going to be able to be dissolved in water, so it'll be soluble. And the smaller it is, it'll be more soluble in water. Conversely, the bigger it is, it'll have a higher boiling point. So here we talk more about intermolecular forces. Again, here we can see the different boiling points. The more hydrogen bonding something has, the higher the boiling point. So you can see here, this nitrogen has little to no hydrogen bonding. This nitrogen here has one hydrogen bond. This one has two hydrogen bonds. So this one's going to have the highest boiling point, then this one, then this one. Okay? Okay. And so now, reactivity. So when we have a dipole-dipole moment, there's going to be a point on a molecule where there's going to be a partial positive charge. So you can see here on this carbon here, this guy has a partial positive charge because all of its electrons are being moved to the side by chlorine, which makes it more reactive. And you see all these nucleophile, electrophile, all of these words will come into more of a play later chapters, more like chapter 5 and stuff, so next test. Recall that nucleophiles and electrophiles are associated with Lewis acids and Lewis bases. Okay, so let's continue on. So what I would think about questions in this type of chapter, I would think naming your functional groups in like one big molecule, telling me what's going to have the highest boiling point, and telling me which one's going to be the most soluble in water. So we can see here, hydrogen bonding. Hydrogen bonding is the strongest intermolecular force. So since this guy here has hydrogen bonding, it's going to have the highest boiling point. And then comes this guy, which has a dipole-dipole moment. And then finally this guy, which only has van der Waals, okay? And recall that all of these will have van der Waals. It's just this guy only has van der Waals, and that's and that's the strongest intermolecular force there. Okay. And let's just keep going. Melting point, again, I wouldn't worry too much about melting point, but generally it's going to go along with the trends of the boiling points. And there was a question in that I was asked in a chat. It had something like this versus this, and it was like, which one is going to have the higher melting point? And it looks like it would be this one, right? Because it can pack together better. However, the way that this bond is shaped, where both of the big groups are on the same side, that's going to make it a little bit more unstable than this guy. So this guy's going to have the higher melting point and all that stuff. That's something that you'll get into later when you get into alkenes, which, a reminder, that's just a molecule with a C-C double bond. Okay. Okay. So solubility, again, if it does have a dipole moment, if it is polar or polarizable, it will be soluble in water. Okay. And also, something else to note, if it doesn't have a dipole moment, it will be soluble in an organic solvent. This is why we see stuff like oil and water not mixing. It's because water is a polar solvent and oil is a non-polar solvent. So if we have something like butane or hexane or something like that, that will dissolve in oil, which is our organic solvent, but it will not dissolve in water, which is our polar solvent. Okay? Okay, so that's it for chapter 3. I'm going to go on to chapter 4, which I feel like is much more important. Chapter 4, alkanes. What this chapter is going over, it's just carbon-carbon single bonds. So anything that kind of looks like this. Okay? Easy. And so let's scroll down. So essentially, something important to note is how we draw alkanes, alkenes, alkynes in the 3-dimensional structure on a 2-dimensional piece of paper. We're gonna draw it like this, where this this solid wedge is something that's coming out of the screen towards us, and this dashed wedge is something that's going into the screen away from us. So it's like if I drew if I drew a pyramid, and you can see here clearly how this point of the pyramid is coming out towards us, and this point of the pyramid is going away from us. This point of the pyramid would be a solid wedge, and this point would be a dashed wedge, okay? And then anything on lines, it's just in the same plane as the paper, okay? And this will come into more, this will become more important when we talk about something called stereochemistry. That's just how a molecule exists in space. Okay, so let's continue on. So we did talk about a little bit how we draw in the line angle structure format. If you don't quite understand that yet, I would go and watch my previous video, DM me, or watch a video on YouTube by the organic chemistry tutor about all this stuff so you can learn how to draw line angle structures better. But I'm just gonna sort of skip over it for now because I feel like there are more important topics to cover in this chapter. So cycloalkanes, these are simply alkanes, which, a reminder, just a something with that has only C-C single bonds. Cycloalkanes are just what happens when we connect one end of a carbon chain to another. So here's a triangle. Obviously, each point is going to be 1 carbon, so we have 3 carbons. Cyclobutane, but means 4, so we're going to have a square with 4 carbons. Cyclopentane, pent means 5 carbons, and cyclohexane, hexane means 6. Okay, easy enough. These will come into more play later when we're talking about substituents. So, okay, so when we're talking about organic molecules, we have to name them in a specific and scientific way so that everyone knows what we're talking about. So like when I say alcohol, you might be thinking, oh, that's wine, beer stuff, but alcohol is just the name of a functional group in organic chemistry. Alcohol, all that means there's a hydroxy group, which is just an OH group attached to something. However, colloquially, when we talk about alcohol, like in a social sense, we're talking about ethanol. So that's why it's sort of important to determine like what we're actually talking about in a systematic way so that people like if I were going out to talk to somebody and I was like, oh, do you want to talk about, or if I was going out to like my lab or whatever, and I said, do you have alcohol? And they're like, what do you mean? And I say, oh, ethanol. That makes a lot more sense to somebody who's like working in a lab, giving you something that you need. Okay, that may have been like a weird explanation or whatever, but that's just why it's important to actually be able to name these things in a systematic way. And here, what's important is there are 3 parts to the name: the prefix, the parent name, and the suffix. Right now, we're not going to be talking so much about the suffix. Just recall that when we talk about alcohols, usually, we'll be changing the suffix. So like when I said ethanol or propanol, hexanol, that stuff, we're changing the suffix. But right now, we're going to be focusing more on the parent name and the prefix. What the parent name means, that just means the longest continuous carbon chain in a molecule. So let's say we had this guy here. There are 2 continuous carbon, or 3, I guess. There are 3 continuous carbon chains in this formula. There's this guy here. There's this guy here. And then there's the longer guy in the middle, right here. So which of the chains is the parent chain? Well, it's going to be the longest one, which is going to be the pink guy. And so then that's what we're going to name our parent name. The way that I like to go about naming stuff is I like to find the parent chain first and then have my parent name there. So I believe there's a chart later that tells you all of the different types of parent chains. Here it is. So this is something that you kind of have to memorize, but honestly, the hardest ones are going to be the first 4, where you have methyl, ethyl, propyl, butyl. But honestly, after naming like a bunch of stuff, you're going to kind of have that memorized. So I wouldn't worry about it too much. Just sort of practice naming and it should come to you easily. So after we name the parent chain, so let's say again that we had, let me move my screen down a little bit. Let's say again that we had this guy here. When I find the parent chain, I always like to number my carbons just so I know for sure like that is my parent chain. So I have 1, 2, 3, 4, 5, 6. So my parent chain is going to be hexane. Okay, that's important. When we're talking about alkanes in particular, we're going to end the parent chain with ane. Okay, so that's hexane. Okay, and then whenever we have a substituent, we're going to end it with YL. So like if instead this hexane was like a substituent, we would say hexyl. Okay, and that's where we're going to come in with this carbon chain here. This carbon chain is made up of 1 CH3 molecule. There's 1 carbon, so that's going to be meth. Our substituent is going to be methyl, okay? And so then our full name is going to be 2-methyl hexane. And that 2 just tells us where the methyl is on the chain. So, and then we went over this in class, but the way to choose which way you're going to number, like I numbered from this side, but how do I know that I'm not going to number from the other side? Well, we know this because we want to give all the substituents the lowest number possible, all of them. So if I had something CH3 here, so I'm going to erase a little bit of stuff here, just so we can see a little bit more of an example. So like, let's say that I had a methyl group here, an ethyl group here, and a, I don't know, another methyl group here. Would I start naming from this side or from this side? That's a rhetorical question. I would start naming from this side because I want to give everything the lowest number possible. If I start numbering from the left to the right, I give these 2, 3, and 5. If I start numbering from the right side, I give it 2, 4, and 5. Numbering from the left gives everything overall the lower number possible, okay? And so then that's why we choose which side to number the way that we do. Okay. All right, so let's continue on. So naming substituent alkyl groups, we kind of went over this already. When we're naming substituents, we take this root name and then we add "il" to it. So methyl, ethyl, propyl, all that stuff. All right. Let's see. So example 1, we've already sort of gone over that. Draw the compounds. So when I'm drawing, I like to always start from the parent chain. I don't look at anything before I look at the parent chain. So here's our parent chain right here, pentane. So I'm going to start by drawing out just pentane. So that's a 5-carbon chain. So 1, 2, 3, 4, 5, pentane. And then now I'm going to focus on the other bit. So I know I have a 3-ethyl. All that means is I have an ethyl group on 3. So I'm going to number these carbons. 1, 2, 3, 4, 5. And 3 is where my ethyl group is going to be. And all I'm going to do is I'm going to draw in my 2 carbons chain. So I'm going to have 1, 2. And so then there's our 3-ethyl pentane. Okay? Okay. So now let's look at 2,2,4-trimethylpentane. Again, we're ignoring that big scary part at the front, and we're just going to focus on the pentane first. This is just like before, a 5-carbon chain. So 1, 2, 3, 4, 5. And so then now we have 2,2-trimethyl pentane. So the 2,2,4-trimethyl. All that means is we have 3 methyls, which is trimethyl, 3 methyls, and then this tells us where it's going to be on 2, 2 again, and then 4. And so now I'm going to number these carbons again. So 1, 2, 3, 4, 5. And so what this means is we have 2 methyls on 2. So 1, 2, and then 1 methyl on 4. So here's 2,2,4-trimethylpentane. See, it's a lot easier than it probably seemed in class. Let's just continue on. It'll let me. There we go. So we're talking about cycloalkanes. All we're going to do is we're going to change the alkane name to cycloalkane. So let's say we just had a hexane. So 1, 2, 3, 4, 5, 6. So this is a hexane. If I took those 6 carbons and I put them in a ring, it would look like this. And the only thing we're going to change about that parent name is we're going to add cyclo to the front. So this is hexane. This here, that's cyclohexane. Okay? Okay, and so when we're talking about naming cycloalkanes, the parent chain is either going to be the cyclo or the straight carbon chain that's coming off of it. It just depends on which one is going to have more carbons. So let's look at these 2 examples. So we can see here that this guy here, this is a cyclohexane, so it means it has 6 carbons. And what's attached to is a propyl group, which has 3 carbons. 6 is greater than 3, so our cyclohexane is going to be our parent chain. If we look over here, we have 1, 2, 3, 4. This is a propyl group, so we have 4 here. And on this cyclo, we have 1, 2, 3, 3. 4 is bigger than 3, so the cyclo group instead is going to be a substituent. And again, we're going to do the same thing that we did before with straight line carbons. For the substituents, all we're going to add is il. So like, let's take our example from before again. If this cyclohexane was a substituent, it would be cyclohexyl. So all we're changing is that suffix from ane to il. Okay? Okay. So let's continue on. So some examples here. So one of the questions that I got a lot in class was, when can we drop the 1? This is an example of where you can drop the 1, but I highly, highly, highly recommend keeping it in your name, because it's better to put extra stuff in your name and get it right than to drop stuff and get it wrong. So like, let's take this example. So we have a cyclohexane, which I know because this is what cyclohexane is shaped like. And that's going to be our parent chain because it's much longer than this methyl group here. So our parent chain is cyclohexane. Okay? And so again, when we're trying to give everything the lowest number possible, we're going to start from 1. So this is going to be 1, 2, 3, 4, 5, 6. So we're starting from 1 on the methyl group to give the substituent the lowest number possible. So this is going to be 1 methyl cyclohexane. And so in this example, it would be valid to drop that 1 because it's implied that the only substituent there is going to be on 1. However, I do not recommend doing that. Some people will, I usually don't. Okay, I'm going to clear this now. And now we're going to work on the next one. So here we have 4 carbons in the circle, the cyclo. So there's 4 here. And then in the chain next to it, it has 1, 2, 3, 4, 5, 6. So this is going to be our parent chain and not our cyclo. So our parent chain is going to be hexane. No cyclo, just hexane. And our substituent is going to be this 4-carbon cyclo. And 4 carbons, that's going to be a bute group. So this is going to be cyclobutyl. And if we number our carbons, let me get my eraser. If we number our carbons on this 6-carbon chain to give everything the lowest number possible, we're going to go 1, 2, 3, 4, 5, 6, and we're going to name this 1-cyclobutyl hexane. This is somewhere where you cannot drop the 1, because if we just say cyclobutyl hexane, we can't assume that it's going to be on 1. So like that's why I don't really recommend doing it for anything, because it can get confusing and you can end up just getting something wrong for something simple and you'll beat yourself up over it. Okay, so let's continue on. So the rotation of the CC sigma bond. When you have a CC sigma bond, which is just a CC single bond, it can rotate freely around it like wheels. So like if you had a carbon here and a carbon here, they're just both wheels. They're allowed to rotate forwards or backwards or wherever they want. However, if you have a double bond, these wheels cannot rotate, okay? So it's sort of a special thing in single bonds that carbons can freely rotate. And this is where we come into something called a Newman projection. At least I think that's the next thing we're getting into here. Yes. So the Newman projection is based on the fact that the carbons can rotate freely like wheels. And all the Newman projection is, it's just a representation of our carbon compound. Hold on, a cat is being a little bit weird. I'm gonna pause the recording real quick. So again, okay, so we're back. The crisis was averted. And so one of the questions here is, will carbon 2 always be in the front and carbon 3 always in the back? That is not going to be the case always. It just depends on what is indicated that the first carbon is going to be, or the front carbon is going to be, and what the back carbon is going to be, okay? So again, just to review about the Newman projection real quick, just to reiterate, the Newman projection is just a way of looking at a carbon-carbon single bond straight on. So if you remember the example from, or not the example, but what I said earlier about these wedges being out in the front and the dashes being in the back, imagine that instead of looking at just hydrogens and carbons, we're looking at a 3-colored triangle that's looking like this. Like this. Where the purple is towards us, the red is away from us, and the pink is just straight in the plane with this carbon. If we were to rotate this so that the carbon was faced in the middle of these 3 things, if we rotated it, then the pink would be up, the red would be to the left, and the purple would be to the right. And that's how we get to a Newman projection. We're just rotating this whole thing from being on the side to being straight on towards us, okay? Okay, and so there are different ways to write Newman projections, because recall that with a carbon-carbon single bond, we can rotate it in different ways. And there's a handy graph that is right here that is telling us how the energies differ when you're in different conformations. So this energy sort of holds for most of the Newman projections, where it's if they are in line with each other, if they're in the eclipsed form, where each atom is eclipsing each other, it's going to be at higher energy than if it's in the staggered conformation, where the atoms are staggered away from each other. In addition, the energy levels of different conformations depends on how big the atoms are that are on the Newman projection, but we'll get into that later. I want to review a little bit more about how Newman projections work. So let's take this example. I'm going to do the same thing that we did last time. I'm going to make chlorine purple, and I'm going to make hydrogen red, and we're just going to deal with this first carbon here, okay? So when we do a Newman projection, the dot inside the big circle is going to be the carbon that we're looking at straight on, and I'm going to call this carbon 1. And then the circle that is surrounding that carbon 1 is going to be the carbon directly behind it, and we're going to call that carbon 2. Okay? And so usually when you're having Newman projections, you're either going to have a peace sign where you look like this, or an upside down peace sign where you look like this. Okay, it just depends on where your line is. If your line is pointing down, like it is here, then you're going to have the upside down peace sign. If your line is pointing up, like it is over here, you're going to have the regular peace sign. Okay, so let's do this first carbon here. So the carbon that we're looking at directly is carbon 1. So we're only focusing on carbon 1 right now. If we rotated it, so we're looking directly at carbon 1, it would look like this upside down peace sign. And that's because the line is going to be on the bottom, and the two forwards and backwards, or the two spokes on the wheel that are pointing towards us and away from us, are going to be on top. Okay, so I'm just going to draw that out real quick like this. Okay. And so now what we're going to do is, what I like to do first, I like to put whatever was on this regular line on either the line pointing directly up or the line pointing directly down. So since we said that this is going to look like this, we're going to put that on the line pointing directly down, and that's a methyl group. So I can just put CH3 at the end, or technically I don't need to do specific angles. And somebody asked in the chat, do we need to memorize energy levels for certain angles? No, you don't. Just know that sometimes it's going to be higher in energy than at other times in different conformations. Okay, so back to this. So if we moved this, if we rotated it around so that carbon 1 was in the middle of this here, the purple would be pointing out here, this side. And you can probably hear my dog barking now. I'm just in a zoo, I guess. This is because we're rotating it in a way to the right, so that we're looking at carbon straight on, and then that would mean that whatever's pointing out towards us is now going to be pointing to the right. And conversely, anything that's pointing away from us is now going to be pointing to the left. And the same thing is going to occur for the spot in the back. This actually is probably the easier part, because whatever was a solid wedge on the back is just going to line up with what was a solid wedge in the front. So CL was our solid wedge in the front, and H is our solid wedge in the back, so they're both going to end up on the same side. H was our dashed wedge in the front, BR is our dashed wedge in the back, they're on the same side. And finally, our ethyl group here was on a line, so it's going to either be straight up or straight down, in this case, straight up. Okay? Okay, I'm going to go ahead and move on and not do this next example. If you do have any questions, again, just message me. Okay, so back to rotational conformations. So whenever you have a big group, it's going to really hate being by other big groups. So like let's look at this example. So you can see here that it still has the general shape of the other graph, where it goes up and down, up and down, up and down. However, the energy of certain conformations is going to be higher or lower than others. So you can see here that this staggered conformation, where the big groups are as far apart as possible from each other, is going to be the lowest in energy. And then here, this is still staggered, so it's going to be in lower in energy than an eclipsed form. But these big groups are near to each other, so it's going to be in higher than energy than in this one. Okay, and so on. And we can see that the one where the big groups are right on top of each other is going to be the one that has the highest energy. Okay, does that make sense so far?
Yeah.
I'm gonna assume yes. I forget that sometimes people aren't going to talk or not want to talk because they are being recorded in this. So, and so that's basically all you really need to know about those Newman projections. Just know how to draw them if you are given a like a molecule and carbon 1, carbon 2. Okay, so now we're going to be talking about something called ring strain. So each one of these carbons is going to have electrons around it. So this guy's going to have electrons, this one's going to have electrons, this one's going to have electrons. The closer those electrons are to each other, the more they're going to repel each other, and the more ring strain is going to be put on our cyclo compound. So you can see here that these are really close to each other. There's going to be a lot of strain there. Then there's this one farther away, farther away, farther away, where the cyclohexane is going to be the more stable out of all of these, okay? Because they want to approach that 109 degree of the tetrahedral, and they get really close with cyclohexane and cyclopentane, okay? And so then that's basically ring strain. What I want to get more, okay, so this is called angle strain. That might be a question on the test for vocab, but I want to go past it and work on something called the chair conformation. So when we're talking about cyclohexanes in particular, which look like this when drawn in two-dimensionally, when we're in 3 dimensions, it's not going to look like this, and instead it's going to take a chair conformation, which are these two. Everyone hates chair conformations. You're not alone, because everybody hates drawing them, even me, because I can't draw them. But anyways, so this is important because they actually show how a cyclohexane will look in 3-dimensional space. So here's a better picture of it. And what I want to focus on real quick is the different kinds of carbons that we have here. So each one of these carbons can be called an up carbon or a down carbon for obvious reasons. This carbon here is going to be above the 2 beside it, so it's going to be an up carbon. This one's below the 2 beside it, so it's down. This one is up, and it just sort of alternates around the ring like this. Okay. And so then each one of these carbons can have 2 substituents. And that substituent can either be axial, or equatorial. What equatorial and axial mean, it just means how it's oriented in space. Axial means it's either straight up or straight down. Equatorial means that it's more out to the side than straight up and straight down, okay? And each one of those carbons is gonna have 1 axial and 1 equatorial. In addition, each one of those carbons is gonna have 1 up substituent and 1 down substituent, okay? So like we can see here in this front carbon that's down, we have a down axial, and an up equatorial, okay? Does that make sense so far? I'm gonna assume yes. I keep asking that, but no one's gonna answer because they don't want to be recorded, and that's totally fine. But anyways, so this one has an axial down, this one has an equatorial up. But how do we know which one's gonna be axial up, or axial down, or equatorial up, or equatorial down? Well, it depends on what kind of carbon that we're attached to. The direction that the carbon is pointing is gonna be the direction that the axial atom is going to point. So we see here, we have a down carbon, the axial is down. We have an up carbon, the axial is up. We have a down carbon, the axial is down, and so on and so on. And hold on, I gotta pause again. Okay, I'm back. And so back to what we were talking about before. So you can see here that the axial is going to match whatever type of carbon that it's on. If it's on an up carbon, that's going to be an up axial. If it's on a down carbon, it's going to be a down axial. And conversely, if you're on an up carbon, it's going to be a down equatorial. Or if you're on an up carbon, on a down carbon, that's going to be an up equatorial. Okay? And so then that's the general rules of drawing a ring structure. Okay. Okay, and so there's something else called a ring flip. I think this is the last thing that I'll have time to go over for today. But essentially what a ring flip is each one of the carbons in the ring is going to shift 1 position, clockwise or counterclockwise. So let's take this example right here. I'm trying to move the group chat, and it's not letting me. Okay, so let's take this carbon compound right here. So I'm just going to number the carbons like we would if we're just numbering a cyclohexane. So 1, 2, 3, 4, 5, 6. So you have 6 carbons in a cyclohexane, makes sense. And then when we do a ring flip, each carbon is going to shift 1 position. So 1 was up here, now it's down here. So we have 1, 2, 3, 4, 5, 6. Okay? Okay, so in addition to notice what happens is the up molecule or the up atom is going to stay up. But notice we're going from an up carbon to a down carbon. So the up atom is going to stay up, but it's going to become equatorial. And the same thing is going to happen with that down equatorial. It is down, it's gonna stay down, but since it's moving to a down carbon from an up carbon, it's going to become axial, okay? Okay. Actually, we do have time to go over one more thing. Let me see if it's here. So when we're talking about how stable a cyclohexane is, when we're talking about the chair conformation, the bigger the atom in equatorial position, the better. Because the equatorial position offers a lot more room for that big atom to take up space, whereas in the axial position, it does not have as much room. So it is more stable when the atom, or the bigger atom, the bigger group, I should say, is in the equatorial position rather than the axial position. And that's why this cyclohexane on the right is going to be more present than the cyclohexane on the left. Okay? That makes sense? I'm going to assume yes. And I'm going to go ahead and stop for today because I got to do some stuff. But again, feel free to message me if you have any additional questions. And I will continue doing office hours like this, but on Fridays at 3 p.m. instead of Thursdays. Okay? So I will see you guys.